We're now ready to implement the expectation maximization algorithm. We're going to look at a couple of details you got to make sure you get right, and then we're going to look at some code for implementing EM for this line fitting problem. First things first, you have to assume that the model parameters are known to bootstrap this whole thing. Now, there's a couple of options here. One option is you do what you did in k-means. You just guess. Just pick some random values. That seems like it's a really bad idea, by the way, but it's surprisingly effective sometimes, but you sometimes can do a little bit better. So for example, one thing you could do is run k-means clustering on this, the hard assignment that maybe is a little sloppy, but maybe that gets you something close to an initial estimate, and then you do something like EM in order to do a refinement because it's probabilistic and you're going to be able to deal with some uncertainty a little bit better. And there's a number of tricks of the trade for how to try to get reasonably good first estimates that we won't go into a lot of detail here about, but know that beyond just guessing some random parameters, there are other tricks that you can do to try to make things a little bit more likely to converge to the answers that you want. Now, the other thing we have to be a little careful about, and I hinted at this early on, was remember that in the E step, we assumed that we knew the probability, the conditional probability of seeing a particular residual given it belonged to a model. And remember that what we said is that that is a statement of how much slop is in your data. How much do you expect these data points to deviate from the model? Now, look, sometimes you may know that. This may be a generative model where you know what the measurement error is, but often you don't know. And here's the rub. If you pick this number too small, the sigma on the Gaussian distribution, then what's going to happen is only points very, very close to the line are going to belong, and everybody else is going to be like, well, that's not me because that's a low probability. On the other hand, if you pick that sigma here, the standard deviation, the width of the normal, to be too large, well, then everybody belongs to the line, right? Because the probability of the residual could be anything. And so it's not immediately obvious what you do here because you don't want to make it too small, it's too restrictive. You don't want to make it too big because it's too welcoming to all data points. And when we go to implement EM, I'm going to show you a simple trick for how to adaptively change this. And the intuition here is going to be you sort of want to start generous and then get tighter and tighter and tighter over time so that as you start to fit that line, you start to take advantage of the fact that you've got a pretty good idea of what the clusters or the model belongings are. And I'll show you what that looks like when we go to do the code. Actually, I'm going to show you right now. So the rule is, and I'm not going to derive where this comes from, but I'll just tell you that on each iteration, we're going to update this sigma. We're going to bootstrap it with a fairly large sigma. That has to get tuned, and you have to be very careful not to be too big or too small to begin with. But then on each iteration, what we're going to do is update the sigma according to this update rule. And let's see what the update rule says to do. Compute the next sigma of the Gaussian distribution used in the E step to be the sum over all data points, I equals 1 to n, of the weight or the probability times the residual squared divided by the sum of all the weights. What is this? This is just a weighted sum of all the residuals. What you are saying is that if the residuals are really big for the data relative to the line, well then the sigma should be big. And if the residuals for the kth model are all really small, well then the probability should be relatively small. And by doing this, we can adaptively figure out what the sigma is as we are iterating through the EM steps. All right, let's write some code. Let's bring in some libraries. Again, this IPython display in time is just because we're going to do some animation. I'm going to specify a number of things. How many data points did I have? I'm going to generate some synthetic data. How many iterations do I want to go over? A maximum number of iterations. What is the noise in the data I'm about to synthesize? And then what is my initial sigma, which I've set to be 0.075 squared. All right, let's generate some model parameters. They're lines. So M1 and M2 are slope intercept randomly generated. And then let's generate some data. So generate a bunch of x coordinates for model 1, and then push that x coordinate through the model, and then add a little bit of noise to that to the data. Same thing for model 2. So x1, y1 are the coordinates for model 1, x2, y2 are the coordinates for model 2, and then pack everything into a matrix. Because at this point, Sure, in synthetic data, I know what the model assignment is, but I'm going to pack everything into a matrix because at that point, afterwards, now it's my job to figure out the model assignment. Plot everything to make sure you didn't screw anything up, and it's going to look something like this right here. And now here I've color-coded because I know what the right answer is. And then our job, of course, is going to be to fit the line, the red line and the blue line without knowing what the initial model parameters are and without knowing the initial class assignment. All right, so that was just to set up some synthetic data. Now let's do EM. And this is it. It's actually pretty clean. So I'm going to just pick some random model parameters, M1 and M2. I'm going to just say, pick a random slope and intercept for each model. And then set sigma to be the sigma that I initialized previously. And remember, we're going to update this on each iteration. You can see that update down here. So I'm setting up a maximum number of iterations. I could have also done this with a while loop and said, please stop when the model parameters don't deviate more than a certain amount. I, again, didn't do that the way I didn't do it in the k-means because it just adds a little bit more code, and I wanted this to fit on one page. In the E step, what do? Compute the residual. That is the vertical distance between the point and the model and the y coordinate. So there's residual 1, residual 2. Notice, by the way, I'm not taking absolute value or squaring. Why? When I go to compute the probability, I'm going to square that residual, so it doesn't matter whether I take the absolute value or not. So remember what the probability was. We compute the conditional probability on the numerator of belonging to model 1 divided by the probability that it belongs to model 1 plus the probability it belongs to model 2, the normalization part. So the denominator is the same for both models. It's the e to the minus r1 squared over sigma plus e to the minus r2 squared over sigma. Notice I don't have the normalization in front of the sigma here or here or here. That's because it's the same on the numerator and denominator, so I can just ignore it. It'll factor out. It'll cancel out. The probability of belonging to model 1 is the exponential divided by that denominator. The probability of 2 is the exponential with the second residual divided by the denominator. By the way, notice that this denominator is just making sure that these things sum to 1, as they should, because they're probabilities. So now I'm done with the E step. I now have, for every data point, I have a probability associated with it. Okay, now we do the M step. So we build our matrix. There's my M matrix, my B matrix. Here is my weighting matrix for W1, my weighting matrix for W2. And here is my weighted least squares estimation. I've got my matrix inverse times the matrix transpose times the data. And of course, I've slammed in the weighting matrices in here. By the way, I didn't actually have to compute W2 here because once I know W1, W2 has to be 1 minus it. I put it in here just so you could see it, but you could make this a little bit more efficient. I now have re-estimated my model parameter M1 and M2. I'm going to update the sigma based on that update rule by looking at what the sums of the residuals are, and then that sig gets re-estimated. This is incredibly important. You should experiment with this code. See what happens when you take the initial sigma up here and make it too small or too big, and watch what happens to the convergence properties. EM will converge, but it won't necessarily converge to the right thing. And here's an example of running the EM algorithm. Step 1, step 2, step 3. I think this is actually step 1, 5, and 10. I've taken snapshots. So notice at the beginning, the model parameters are not particularly good, right? And notice the class assignments. So why are these red points up here belonging to the red model? Because they're closer to the red line. And every point is being assigned probabilistically closest to the line it belongs to. And after just a couple of iterations, we get to here, we're doing pretty good, and then eventually we get to here and we've done a really good job. There is a couple of things you should know about EM. It is guaranteed to converge. There's a proof of this. We know it will converge. I can't tell you exactly how long it will take to converge, and more importantly, I can't tell you that it'll converge to the right answer. We don't know that if you have 2 discrete clusters because you can get unlucky. You could pick some really bad starting conditions and it will get stuck in a weird local minimum. And here you have to play the same game that you do with k-means. You need to start with different random conditions and look at the distribution of the class assignments and then do some type of voting to figure out what are the ones that are most representative of the data. Like k-means, EM has its place, but it also has its limitations. First of all, you need to have a model of your underlying data, a cluster center, a line, a parabola, a plane, a hyperplane, whatever it is. You are vulnerable to starting conditions. If you get good starting conditions or you have some prior knowledge, EM can be a very powerful tool. You are vulnerable to that probability distribution. If you don't have a good estimate of the slop in your data, you can either be too conservative or too liberal in your estimations. But both k-means and EM are very powerful and really basic techniques for exploring data to try to determine how to do unsupervised learning, how to simultaneously learn your model parameters and the assignment to those model parameters. Like k-means, EM also has a mechanism for not having to specify exactly how many classes. And the basic idea goes like you start with a large number of classes, and then as the classes collapse onto each other, you start to trim them back. And if you go into the literature, you'll see a variety of tricks that makes EM a little bit more efficient and a little bit more effective. But that's the basic idea. So k-means is, we can think about that as a hard EM, and EM is a soft k-means. They both have their strengths and their limitations, but they are both computationally very efficient and have a place in your toolkit for doing unsupervised learning.